Good evening, everyone. My name is Harini. So, I'm a PhD scholar from Indian Institute of Science in Center for Water Research Department. So, I'm currently handling NPTEL TA-ship offered for the course Watershed Hydrology by Professor Rajendra Singh sir from IIT Kharagpur. So, now in today's lecture, we will be talking about stream flow and also how we measure the stream flow and how to estimate the storage and the demand of a reservoir, also how what is flow duration curve and flow mass curves. These are the main topics of our lecture today. Okay, so first coming to stream flow, as we all know that this is the visible component of an hydrological cycle. So the definition for stream flow is that stream flow refers to the volume of water passing through a fixed location on a stream, and its units are measured in meter cube per second or cumex. So the definition is stream flow refers to the volume of water passing through a fixed point in a river, and generally it's measured in meter cube per second or cumex. Okay, so we all know that the precipitation is the main source of stream flow, right? So what are the different stages that will take place from for the precipitation to get converted into stream flow is shown in this flow chart. Okay, so first, when the precipitation occurs, there is a part of precipitation that falls within the river channel. Okay, so that is called as channel precipitation. Okay, which will contribute to stream flow directly, right? So then a part of precipitation will fall on the surface of the earth. That is called as overland flow. Okay, so this water that falls on the surface will be flown as surface runoff, and finally it will reach the streams and the flow will be stream flow. Okay, so and in some cases what will happen when there is water getting stored in the depressions in on the surface or on the vegetative surface, the water will get infiltrated into the soil. So whatever water that got infiltrated will flow through the soil profile as interflow, and part of this infiltration water will be percolated deep into the soil, into the deeper layers of soil, which will be stored as groundwater. Okay, and this interflow, whatever water that is flowing on the on the lateral movement of water into this in the soil, there are two types, which is rapid interflow and delayed interflow. As the name suggests, the movement will be quick in rapid interflow. So this rapid interflow, whatever water that is flowing in the soil, will finally come onto the surface at some point, and then it will reach the stream flow. Okay, so and the other type of interflow is delayed interflow, where water will not get percolated into deeper layers, but there will be a slow rate of flow, and this flow will be occurring in the subsurface area of the soil. Okay, so the runoff is called as subsurface runoff, and this will be finally going into base flow, which will again come and join into the streams as stream flow. So here we can see that the major sources of stream flow is channel precipitation, overland flow. Whatever water that we are getting from infiltration and finally as stream flow will take longer duration, and also the amount of water that keeps coming into the stream flow will be also very less. Okay, So now coming to few of the definitions, we have that surface runoff. So first, surface runoff is defined as portion of precipitation that falls over the ground surface, and ultimately it will reach the streams, rivers, or lakes or any other water body without infiltrating the soil. This is called as surface runoff. Okay. Then we have base flow. So this is the constant rate of flow that will come from the subsurface or groundwater flow. Okay, the constant rate of flow that comes from either subsurface runoff or groundwater into the streams is called as base flow. Then we have term called interflow. Interflow is defined as the lateral movement of water within the soil profile. Okay. Here we have, as we have discussed, there is rapid interflow, and also we have delayed interflow. So rapid interflow means there is a swift movement of water through the soil profile during or immediately after the intense precipitation event. Okay. And delayed interflow is that there is a gradual movement of water through the soil profile. So in rapid interflow, the flow rate will be higher compared to delayed interflow. Okay. So here we can see that the water, whatever precipitation that occurs in this diagram, it is clear that when the water is flowing on the surface, it is called as overland flow or surface runoff, and a part of the water is flowing lateral motion within the soil profile. This is called as interflow, and whatever water that got infiltrated into the groundwater or this interflow will be contributed to the base flow, and this water will finally reaches the stream network. Okay, so then we have another term called variation of process within the precipitation event. Okay, so here we can see that as the uh, duration of the time since the precipitation began, as the time is going on, we will be seeing how the various processes within the hydrological cycle are changing. So initially, whatever precipitation that has occurred in the channel will be 100% contributing to the uh, stream flow, right? So this rate will be constant throughout the time period. And then a part of that will be, and also we have learnt in the first class that there are abstractions that occur whenever there is some precipitation. So the abstractions are interception and evapotranspiration, right? So this will be constant throughout the time because interception is due to the because the water droplets get stick to the subsurfaces. This is interception, and also evapotranspiration. These two remain constant with time. When we consider there is not much daily fluctuations in the temperature. Okay, and we can see that as the time increases, there is a decrease in the infiltration rate because as the at initial stages we can see that the soil might be dry, so there will be infiltration rate will be higher, and as the time keeps go on, there will be constant infiltration that keeps happening. So there will be a decay, as we have still learned in Horton's equation. So, and then we can see there are two terms, surface storage and soil moisture storage, right? So the surface storage, in these two terms, we have two definitions, two classifications again, retention and detention. What is retention? Hmm? So retention is that storage held for longer period of time and depleted by evaporation. This is called as retention. And there is one more term, detention. Here we should concentrate mainly on this term called longer time. When the storage is held for longer time, it is called as retention. And if it is short term storage, it is called as detention. And in case of short term storage, the depletion occurs by flow away from the storage location. Okay. Is this clear? What is retention and detention? And from these, so in surface storage, whenever there are depressions or anything, depressions or leak is an example of depression. So in that, the water will be stored for a longer period. So the water stored in that lakes is called as retention. And when there are very small depressions like potholes or anything, the water will be stored for a shorter period of time. And if the precipitation value is more than the volume that it can accommodate, the water will flow away from the depression, right? So it's a short-term storage and it's called detention. And in case of ground moisture storage, also we can see the terms retention and detention. So, for example, in soil moisture storage, the water that is stored in groundwater, it will take longer time, like it will take years for the water to reach the stream flow. So there, that is an example for retention. And in case of like subsurface flow or any other flow, it is called as detention, or the soil moisture at the top layer of soil is an example for detention, because due to evapotranspiration the water in the top layer of soil will get evaporated quickly. So it's an example of detention. Okay, we can see that both soil moisture storage and surface storage are reducing with time. Also, then we have three more terms called as overland flow, unsaturated flow, and groundwater flow. Okay, all these terms will lead to channel flow. Okay, so as we discussed earlier, overland flow is the flow that is occurring on the surface of the earth is called overland flow, and the unsaturated flow is water that is occurring in the unsaturated soil profile is called as soil layer is called as unsaturated flow. And in case of groundwater flow, the water will be occurring in the deeper layers of soil. It's called as groundwater flow. Okay. Then mainly when we are studying hydrology, we will concentrate on the term called how much of precipitation gets converted into stream flow. This is what we are interested, because based on the amount of stream flow that is generated, we can do water supply management, and also environmental conditions of an area depends on the water available, and also like estimate risk, like for floods, droughts. In these cases, um, how to apply mitigation measures, etc. We all will know once we get the details of stream flow. Okay. So now here we will be talking about stream flow generation, where, as we have talked, we have like mainly three flows. Okay. First one is overland flow. Okay. And second one is groundwater flow. We can see that the water is percolating into deeper layers of the soil in this case, and then there is a flow occurring laterally to join the streams, right? This is called as groundwater flow. And this is the third one is subsurface flow, where flow will be occurring in the top layers of the soil in the lateral direction. Okay, and these will uh, after few days it will also join the stream flow. And then fourth term is saturated excess rainfall, overland flow. Okay, so what is saturated excess rainfall? All these terms we will be discussing in the next minute. So first is infiltration excess, Hortonian overland flow. Okay, so when we neglect interception by vegetation, the surface runoff is that part of rainfall which is not absorbed by the soil by infiltration. This is called as uh, Hortonian excess rainfall. Okay, surface runoff, that is part of rainfall which is not absorbed by the soil by infiltration, is called as infiltration excess overland flow. So here in this figure also you can see that whatever water that is falling first is getting infiltrated, and the excess amount of rainfall is flown laterally on the surface. This is infiltration excess overland flow. Second one is, okay, so in this case, whenever the rainfall intensity is less than infiltration capacity of soil, the excess rainfall is equal to zero. If the rainfall intensity is more than infiltration rate, then excess or effective rainfall is equal to I minus F. Okay. So here what will happen is the whatever the water is flowing, we can see that it's flowing as a sheet. Okay. And also along the overland flow, there is a depression storage that can occur, and also surface detention storage that can also occur, because whenever the water is flowing, wherever the depressions are there, it gets stored. So that's why depression storage and surface detention storage can occur. Okay, and Hortonian overland flow will occur only in these cases when the surface is impervious, and also the natural surfaces which has very thin soil layers and has low infiltration capacity. The Hortonian overland flow can be seen. Okay, this rarely occurs in vegetation covered areas. So secondly, we will be talking about saturated excess overland flow. Here you can see that till now we talked about a Hortonian overland flow. We can see that whatever water falling as precipitation is flowing on the surface when there is a saturation occurred in the soil. In Hortonian case, what will happen is, here also you can see that the arrow is coming from the surface. When the top surface get saturated because of this subsurface flow, the water will come out of the surface, which will contribute to surface runoff. This is called as saturated overland flow. So in Hortonian case, saturation from above by infiltration is happening. Okay, as you can see here it is saturated, and as we go down it's a dry soil, so by infiltration the saturation is occurring in the soil. And in case of saturated excess, saturation from below by subsurface flow or groundwater flow. You can see that in this part there might be subsurface flow or groundwater flow which is saturating the center soil, and the water will be coming in onto the surface. This is called as saturated overland flow. And thirdly, we will be talking about subsurface flow. This refers to movement of water beneath its surface within the soil or rock layers. Okay. So what is happening is when the rainfall is occurring, this part of soil will get infiltrated and get saturated, right? So, and this distance is less, so the flow will occur like this. This is called as subsurface flow. Okay. So primarily this will occur in vegetation surfaces in humid areas where intensity is less than infiltration capacity, and also it is a very slow process. It will contribute, the contribution is negligible to the stream flow, and it occurs in both saturated and unsaturated areas. So here you can see that this area is saturated but this is unsaturated. But due to difference in head, the water will flow in these directions. So there is a flow in both saturated as well as unsaturated regions. Okay. Now we will be talking about types of streams. So first one, based on runoff characteristics, there are three types of streams. First one is ephemeral. In ephemeral streams, there will be flow only during or after a storm. Okay. Stream carries flow only during or after a storm event. So we can see highly variable flow that can occur in ephemeral streams. Then second we have intermittent streams. The streams in these streams, the flow will be occurring during monsoon seasons only. Stream carries flow during monsoon season. So we can see there is a seasonal variation in the flow that can occur in intermittent streams. Next we have perennial streams. These will carry the flow throughout the year. Okay. For these rivers, the main input for stream flow is not only the rainfall, it might get, because suppose if we are receiving rainfall in monsoon season, in summer season, these river get stream flow input using from snowmelts. Also, groundwater also sometimes contribute to the stream flow in these rivers. The example for perennial river is Ganga in Indian basin in India. And then there is one more classification for the types of streams. It is based on flow of water and structure of river networks. So in this we have two types of streams. One is affluent stream, also called as gaining stream. Okay. In this, the groundwater will contribute water to the stream. Hence, the stream will expand deeper and also broader. Okay. Groundwater contributes water to the stream. This can be seen mainly in tropical and temperate climate. And the second type of stream is influent stream or losing stream. So this stream will contribute water to other water body. Stream that contributes water to other water bodies. Okay, this type of streams mainly you can see in arid regions. So now let's see some questions related to this topic. Uh, Till now we have discussed different terms in stream flow like base flow, interflow, etc. And also we have discussed about types of streams, right? So the first question is, the lateral movement of water within the soil profile is termed as option E interflow, option B base flow, option C is stream flow, and option D is runoff. Any answers? So the answer is interflow. Okay. So if you have any questions in middle, you can raise your hand or you can switch on the mic and ask questions. And the second question is, storage held for a longer period of time and depleted by evaporation is termed as option E surface detention, B surface detention, option C is soil moisture detention, and option D is soil moisture retention. So whenever we see the longer period, it is a retention, and in only in surface retention, the depletion can occur by evaporation. Okay. So, the third, coming to the third question, if the rainfall intensity exceeds the infiltration rate, the effective rainfall will be equal to. Okay, this we have studied it infiltration chapter as well. Whenever rainfall exceeds the infiltration, the excess rainfall will be equal to I minus F. Okay. Then in next question, if the rainfall intensity exceeds the infiltration rate will be equal to option A, rainfall intensity, option B, potential infiltration, option C, interflow, option D, ponding depth. So the answer is potential infiltration. So we have also talked about saturation excess flow, right? So the question related to that is saturated excess rainfall occurs due to option A, saturation from above by infiltration. Option B, saturation from below by subsurface and groundwater table. Option C, saturation from both above and below of the surface. And option D is none. So in case of overland flow, the saturation occurs from above, but in case of saturation excess, the saturation occurs from below by subsurface and groundwater table. So the next question is based on runoff characteristics of the stream. Ganga River can be classified as which type of stream? Option A, ephemeral stream. Option B, intermittent stream. Option C, perennial stream. Option D, none of this. So Ganga River has flown throughout the year. So it's a perennial river. So now let's talk about stream flow measurements. Why do you need to measure stream flow? So, as we have seen that stream flow, by measuring the stream flow from that data, we can do water supply management. Also, we can predict risk and apply some mitigation measures, and also how what will be the environmental conditions. All this we can learn from the streamflow data. So for the streamflow measurement is a process of quantifying the magnitude of water within the stream, river or other water sources. Okay, this is called as streamflow measurement. And study of streamflow measurement is called as hydrometer. Okay, and we have various methods by which streamflow can be measured. Okay, so few of the main important types are there are direct methods and indirect methods. Okay, in direct methods we either calculate velocity or directly discharge using some techniques called area velocity method. Second one, electromagnetic. Third one, dilution technique. Fourth one, ultrasonic. And in case of indirect methods, we use hydraulic structures to take indirect measurements. Like based on the head, we will have some formula, and using that we will calculate discharge. So in hydraulic structures, for example, we use weirs, flumes, and gated structures to get indirect measurement of stream flow. And another method is slope area method. Okay. So generally from mostly what we will be doing is we will be using stream gauges which will measure the flow in the rivers or streams. Okay. Based on this flow or discharge value and the height of the water within the reservoir or stream or dam, we will we will get a curve which will relate the discharge and elevation within the stream. So as the discharge is increasing, obviously the depth of water in the river should increase, right? So it is a increasing curve, and this relationship is called as stage discharge relationship. Okay, so once we get this discharge data from stream gauges, and also we have the elevation head of the water, we will get this plot for each stream or river at a particular location. And what we will do is, suppose in future case, once this relationship is established and we know that this much some 100 meter cube per second amount of discharge is happening, we will know what is the height of the water in the river. Or else, suppose we know the elevation head of the river, suppose some 10 meters of 10 meters is the elevation head in the river, then we can find the discharge values within the stream. Okay, so here first we will be talking about, to get this relationship we need to calculate measure the sorry, elevation, right? That we will first see how we will be measuring the stage or elevation. Okay, first we will be talking about manual gauges. In manual gauges, we have staff gauge. Okay, first one. So staff gauge is nothing but like, it is like a long vertical or marked ruler which can be made of wood, metal, or fiberglass. And it will be, we will just put that ruler into the stream and we will measure the depth. So we'll can get the stage measurement in feet, meter, inches, or centimeters. And sometimes what we will do is we will anchor it to a structure, like in dams we will have a big, or in a pillar we will just put the measurements of the height, right? And based on the water level we will know the based on the top surface of water which is touching the pillar, we can take the measurement. That will give us the elevation of water in the stream. And we have, other than staff gauge, we have wire gauge. So as the name itself suggests, what we will have is we will have a wire rolled around the drum, and what we will do is we will try to put the wire into the water till it touches the surface from the above. So based on the rotation of the drum, we will know the length of the cable, that wire that has gone, and which will give us the elevation value of the river. So both these gauges, staff gauge and wire gauge, are non-recording type. So next, let's see few examples of recording type. In recording type, we have automatic float gauge recorder. It is similar to the floating type recorder in the rain gauges, where based on the water that is flown into this gauge, the float will give us a reading, and this will help us to make the reading. Okay, and the main advantage of this is that we have a stilling well which will prevent the debris from entering into the gauge. So, and also based on the movement of the float, the pen will record as the measurement, and this will be used for later stages. Okay, and another type of recording gauge is bubble gauge. So in bubble gauge, what we will be doing is we will be sending a compressed gas through a channel to the bottom of the riverbed. Okay, once we see the bubbles coming up, we know how much of pressure we have used to send the gas, right? And based on that gas pressure, we will get the elevation of water. So the whatever the gas pressure that is recorded using manometer or pressure transducer will be equal to pressure in the orifice plus elevation at. Okay, sorry. Gas pressure is equal to pressure plus elevation head at the orifice. Okay. Now you understood how we will get the stage measurements using manual gauges and recording type. And from this elevation, what we will be doing is we will be developing a discharge relationship, which is also called as rating curve. So also we will be seeing that when the discharge will be affected in the rivers due to the changes in flow characteristics owing to changes in channel due to dredging, weed growth, or sedimentation. So when there is some sediment get stored in the dams or reservoirs, what will happen is the elevation head will increase. But we will be thinking that if this is the if 10 meters is the elevation head, this is the discharge. But due to the sediment that has occurred on the ground surface, the actual elevation will be lower than that. So there won't be the discharge that we are calculating using this rating curve won't be correct. So the rating curve has to be updated every time because of these conditions. Because of weed growth, the relationship will change. Also because of sedimentation, deposition, etc. So we need to keep updating this rating curve. So now we will start with direct measurements of stream flow, and the first one is area velocity measurement. So as the name itself suggests that what we will do is we'll calculate discharge using a relationship called area into velocity. Okay, so this is cross section area of the channel, and velocity we will obtain using some instruments like current meter, for example. Okay, so the main assumptions in area velocity method are the flow should be steady and uniform. Then only we can apply this area velocity method. Okay, and also we assume that constant channel shape, because if the channel shape changes, the area also changes, right? Area of cross section changes. And we consider there is negligible backwater effect. And we can say also assume that there is negligible side contraction and expansion effect. So as we have discussed, the velocity is measured using an instrument called current meter. Okay, so in this we will have conical cups that will rotate, and which will be proportional to the velocity of water. Okay, conical cups within current meter rotate, which will be proportional to velocity of water. So we have two types of current meters. One is vertical axis and another one is horizontal axis. So vertical axis means the rotation will be occurring in horizontal, and in horizontal axis the rotation will be occurring vertically, right? So in vertical axis will have a series of conical cups mounted around a vertical axis, and this is useful when the water velocity is in between 0.15 to 4 meter per second. Okay, so the example flow for this is price type and pygmy type current meters, and in case of horizontal axis we have propellers which are mounted at the end of horizontal axis or horizontal shaft. So the advantage of horizontal axis current meter over vertical axis is that it causes lesser disturbance to flow. So it is less sensitive to vertical velocity component. And similarly, it can also be used when the flow velocity is in between 0.15 to 4 meter per second. Okay. And we already discussed that based on the conical cup rotation, we will be calculating velocity, right? And the relationship between that velocity of river is equal to A into N plus B. A and B are constant. Here N is number of revolutions per second of the meter. And V is stream velocity at that location. Okay, and A and B will be mostly given based on when we are buying the instrument itself, we will get what is the value of A and B given by the company itself. So also the velocity in a stream in vertical direction won't be constant. Okay, so if this is the water surface and this is the ground surface of the stream, then we can see that the profile of velocity is like this. This is vertical profile of velocity. We can see that the maximum velocity doesn't occur on the surface of the water. It occurs just below the water surface. And here this is the velocity at the surface. This is lower because of the friction between water and air. So we see slightly less velocity on the surface of the river. And here at the bottom of the river, we see the lowest velocity due to drag between the water and the rough surface, that is ground surface. Okay. And what so in case of shallow rivers, that is when the depth of the stream is less than 3 meters, we calculate average velocity is equal to velocity that is measured at 0.6 times the depth of flow below the surface. Okay, so if we keep instrument at 0.6 meters 0.6 times the depth of the river, and we take a measurement at that location, this will be the average velocity of the shallow water stream at that particular location of the stream. Okay. If it is deep streams, that is, if the depth is greater than 3 meters, the average velocity will be equal to the velocity measured at 0.2 times the depth of the stream from the above plus velocity measured at 0.8 times the depth of the stream from above by 2. So we take average of the velocity that is measured at 0.2 times the depth and 0.2 times the 0.8 times the depth from the above. Okay. So in case of large streams, what we will be doing is we will have a ropeway and current meter. Together, we will be measuring the flow velocity at different points across the uh, cross section, because across till now we talked about how the velocity varies with respect to depth, right? So allow across the cross section also the velocity will vary, so we have to take multiple measurements in case of large streams. In large streams, flow velocity is measured at different points in a cross section, and using that measurement we will calculate the average velocity of the cross section. Okay. So how do we know whether the stream is shallow or deep? uh, so based on the depth, right? How do we measure the depth? Using sounding rods or sounding weights, we can measure the depth of the stream in case of shallow streams. In case of deep streams, we have to use echo depth recorder. Okay, in echo depth recorder, we will be sending the sound waves and the time interval between the signal received back, that is the whatever the sound wave that we have sent from above will get reflected from the bottom of the river surface, right? We'll calculate the time taken. Based on that, the depth of the river will be estimated. So in case of these large streams, as we have discussed, we will calculate, will measure the velocity at different depths at across different points in a cross section. See here we have at y1 in this particular section, we have taken a measurement at y1 depth and at y2. Similarly, as the depth is increasing, we need to take measurements at two locations, that is 0.2 times d and 0.8 times d. So like this, we will be taking measurements in a large streams network. Okay. So in this case, first what we will be doing is we are cutting the cross section into n minus 1 sections as shown in this figure. Okay. And total stream flow will be equal to sum of the stream flow that is calculated in each section of this n minus 1. Okay. So here I am just writing the formula related to this because the detailed methodology is discussed already in the class. Okay. For I equal to 2 to n minus 2 sections, the flow within the section is calculated by this formula, pi into vi bar. Okay. So this is area of the cross section that is calculated using trapezoidal rule, and this is the average velocity. So as we have discussed, this average velocity, suppose if the depth is shallow, then we will only measure at 0.6 times d, and if it is deep, we will take multiple measurements and calculate the average of it That will be our average velocity at this particular section. Okay. And here you can see Wi is the width between the two measurements that are taken. Okay. Wi is the width between I minus 1 and ith measurement. Okay. And Yi is the depth of the stream at ith location where we are taking measurement. Okay. In case of end sections, the formula will change. Okay. So here delta Q1 is equal to 1 by 2 W1 plus this is here we are calculating in case of end section, as you can see it's a triangle, it's mostly triangular in shape, so we are using triangular formula to calculate area, and then we will multiply with the average velocity to get the discharge, right? So here what will be the h is this value, and how we will get that h? From singular triangles method, when it is W1 we have Y1, right? When it is this entire length is W1 plus W2 by 2, this is H. Okay. From similar triangle formula, W1 by Y1 equal to simplifies H equal to okay. Once we substitute that, then the flow within the first section is calculated as W1 plus similarly we'll get flow in the n minus 1th section as well. So this is how, after calculating the flow in each section, we'll add it up to get the flow in the entire cross section of the stream. Okay, this is how we calculate stream flow. We'll take stream flow measurement using area velocity method. Now let's look into few questions related to stream flow measurement. So the question is, the ordinate of a rating curve is, ordinate means y-axis, okay, and x-axis is called as abscissa, okay. So in case of rating curve, it's a plot between discharge and stage or elevation, right? So here we have options: water stage, discharge, flow velocity, and rainfall intensity. So the y-axis is stage, so answer is water stage. And the next question is, which of these is not a stage measuring instrument? So the first one is staff gauge. We discussed that it will be a vertical ruler which will be used for measuring the stage. And second option, wire gauge, wire, which will be which is also used for stage measurement. And we have weir and bubble gauge. Okay, even in bubble gauge, we will be measuring the stage, right? So by sending a compressed air through the channel. So the option is weir. Weir is not used for stage measurement. We'll get the discharge measurement using weir. So the average flow velocity in channels, the next question is, the average flow velocity in channels is measured at a depth of Option 1 is 0.6 times the depth of the channel. Option B, average of 0.2 times and 0.8 times the depth of channel. Option C, any of A and B. Option D is none of this. So the first case 0.6 times the depth of channel from above is applied for shallow streams. And in case of deep streams, we will take an average of 0.2 times and 0.8 times the depth of the channel, the flow velocity. So the answer is any of A and B. Okay. So here they are asking to calculate this charge in a stream using the following data. So A equal to 0.51 and B equal to 0.03. And we can see that the discharge distance from the left edge is given and the depth of the stream at each location is also given along the cross section here, and also the revolutions of the current meter kept at 0.6 meters depth. 0.6 times the depth is given and duration of the observations. So here you can see that the depth of the river is not exceeding 3 meters. The maximum depth is 2.5 meters. So this means the river is a shallow river. So the measurements at 0.6 times the depth of river is enough for us. So, and here they have given revolutions and the duration of the revolution. So to calculate velocity, we have formula A equal to V equal to A into N plus B, right? So here B is number of revolutions in seconds. So to calculate N, we need to first divide number of revolutions by the duration of the flow. And once we calculate that, we will substitute in this formula V equal to A into N plus B. A is given as 0.51 meters and B is given as 0.03 meter per second. Right? Using this formula, we'll get velocity. So this is how you will calculate velocity at a particular location in the stream. And as we have discussed earlier, at each at each section of this channel, we will calculate the discharge using the formulas like delta Qi equal to Yi into Wi by 2 plus Wi plus 1 by 2 into Vi bar. Since there are zero velocity at this end sections, that is first and n minus 1 section, I'm not calculating that, but for intermediate sections we have a flow velocity, right? So that how we will calculate, first we have to calculate Wi by 2 plus Wi plus 1 by 2. So for second section, Wi by 2 is, we have a width of 2 meters, 2 by 2 plus also I plus 1, Wi plus 1 is also 2 by 2. And the depth of the river is given as 1.1 into, we calculate average velocity using formula V equal to An plus B, right? And that value is 0.229. Then once we multiply it, we'll get discharge as 0.504 meter per second. Okay. This is how we calculated for second section. Similarly, we do for third, fourth, fifth, sixth, seventh, all this. And once we get the discharges, what we will do is we will add these discharges up. The total discharge is equal to 0.504 plus 1.304 plus 2.055 plus 1.344 plus 0.884 plus 0.366. So the total discharge is 6.457 meter cube per second. Okay, this is how we calculate. Now, now coming to next question, the depth of the flow at a vertical in the stream is 3.5 meters. So since the depth is 3.5, it's a deep stream. Okay, and the velocity of the flow at various point on the vertical is measured by a current meter and is given below. Determine the mean velocity using the 3-point method. So when it is a deep stream, we already learned that V average is equal to V 0.5 times 0.2 times the depth plus 0.8 times the depth by 2. Here, so 0.2 times the depth 3.5 is 0.7 meters. 0.8 times the depth is 2.8 meters. Okay. So here this 0.7 meters is from the top surface of the water, right? 0.7 meters and 2.8 meters. This is the ground surface which is at 3.5 meters. Here they have given the position of water meter above the stream bed. Bed means this one. So when we are calculating this point will be a difference of 3.5 meters and 2.8, that is 0.7 meter. And this is from the bed 2.8 meters. Okay, these two values we will be taking. So V average equal to 3.5 meters per second plus 2 by 2. It is 5.5 by 2, 2.75 meter per second. So this is the average velocity in that particular cross section. Okay. Now let's look into other type of stream flow measurements. So now coming to another type of direct method of stream flow measurement is dilution technique. Okay, it is a chemical method in which a tracer or a chemical will be injected into the stream, and we know the concentration of the tracer that we are injecting and what rate also. And at one particular point we inject, and as the stream is flowing, we make an assumption that the tracer is completely mixed with the flow. Okay, and then we will calculate we will take sample from downstream of the river, and we will calculate the concentration of flow there, concentration of the chemical. So based on the concentrations at 2 points, we will establish a relationship and we will calculate stream flow. So there are mainly three types of tracers. So main things that we have to keep note is that this tracer should not be chemically active, that is should not affect humans or animals life by drinking the water which has these traces. Okay, so first one is we have chemical traces. For that we have examples like NaCl, sodium chloride, sodium dichromate and all. Since the electric conductivity of the water will change when we put these salts, we will use electrical conductivity meter to take measurements. And we have radioactive type. For example, bromine 82, sodium 24, iodine 132. So these are also some type of tracers. And finally, we have fluorescent dyes. So, rhodamine, water tracer, and sulfur rhodamine are the example for this. So, they have a color to it. So, based on the color, we can judge the concentration of it. So, in dilution technique, we have mainly two types of dilution technique. One is constant rate injection of these tracers. Okay. So, in this, what we will be doing is we have a relationship. Okay. So here suppose C naught is the concentration of the chemical that we are injecting at Q2 rate, okay, into a stream which has initially the stream flow Q1 and the concentration C1. Okay. At some point in the downstream, the flow will be Q1 plus Q2 and the concentration will be C2. Okay. So we can measure this concentration by taking a sample from the river and we can measure the concentration. So the Q2 is equal to, using this relationship, we will find the uh, flow at a point in the downstream. So we can see in this case also in concentration, constant injection rate, the concentration of the tracer will slowly increase and become constant, which will be C2, and then it will slowly start decreasing. Secondly, we have slug injection. In this case, a known mass of tracer will be injected into the stream. Okay. And flow is calculated by mass by area under curve. Okay. So here we can see that the concentration of the tracer will peak and then it will decrease. Okay. This area under curve is used, and mass divided by the area under curve will give us the discharge. Okay. So next we have electromagnetic type method, where flow velocity will be measured using a Faraday's law. So the Faraday's law states that the motion of water flowing in a river cuts the vertical component of the vertical component of the Earth's magnetic field, and an electromotive force is induced in the water. Okay. So so we will bury a coil under the surface of the riverbed, and we'll get a flow and the electric potential relationship as Q equal to K into E dash H by I to the power of N. So here E dash is electrode potential, I is coil current in amperes, H is depth of flow in meters, K and N are system constants. Okay. And the main thing is the whatever potential generated here will be proportional to width of the river in meters into magnetic field into average velocity. So that's why we don't see terms like width of the river, velocity in this relationship. Okay, we see that there is electrode potential which is taking care of the width of the river and the average velocity. Okay, The main advantages of this is it's non-intrusive. So when you are putting a chemical, it will get mixed into the water, right? But the whatever potential that is generated and the coil we are keeping, it will be non-intrusive, and there won't be any disturbance to the flow. And also it is adaptable to silty or moving beds. So if the cross section of the channel changes, it doesn't affect the flow measurement. So in case of area velocity method, saw that the cross section should be constant. It should not change with time or with time, right? And also the third advantage is we can do continuous monitoring using electromagnetic method. But the problem with it is very expensive, and so it is used for the rivers with more than 30 meters width. And the mainly it's expensive because we have to insulate the channel, because if it is not insulated, the electricity will get passed into the water, which will be conducted, and the it will result in death of animals, or water, I feel, even for human beings. And the next method is ultrasonic method. It is also a type of direct method where we'll be sending sound waves at an oblique direction of 45 degrees or 60 degrees across the river. Sound waves are sent obliquely at 60 degrees or 45 degrees across the river into the to the opposite direction, and the difference in time is measured using transducers, which will help us in measuring the stream velocity. Okay. And the average depth of flow is measured using float recorder or equivalent instrument. And since we have the depth of the cross section and flow velocity, we can use a area velocity method and calculate the stream flow. Here the stream flow is equal to L square. So here L is the length of the path, and D bar is the average depth of flow along AB, and VL is the stream velocity. VP is the component of stream velocity, which are terms in this. And C is the velocity of sound in meters. And theta is the angle at which we are sending the sound wave. So mainly it is useful for rivers with more than 300 meters depth, and we don't have to establish a where we don't have a stage discharge relationship. This is useful, and when even if the stream has backwater conditions because of dams, tides, or any other causes, this method is applicable. Also, we have another method called acoustic Doppler current profile. In this also, we use advanced instrument to measure the flow velocity in large streams and water bodies. It has four transducers assembly, and these use sound waves and Doppler effect to measure the 3D velocity. So that is like you across a section and across the depth of the section, you will get the velocity. Okay, and so now we have talked about different other types of direct methods which are used for stream flow measurement, like dilution technique, electromagnetic method, ultrasonic, and acoustic Doppler. Now let's look into few questions. So in the first question, they are saying that 20 gram per liter solution of fluorescent tracer was discharged into a stream at a constant rate of 0.00002 meter cube per second. The background concentration of the dye in the stream was 0, and at a downstream section, the dye reached an equilibrium concentration of 10 parts per billion. Estimate the stream discharge in meter cube per second. So here we have known that the using dilution technique, the formula is Q1 in Q2 equal to Q1 into C2 minus C1 minus C0 by C2 minus C0. Okay. So here they are saying that initially the concentration in the river is 0 and the flow is this into initial concentration is 30 gram per liter, and finally there is a concentration of 10 parts per billion. Okay. 10 parts 1 ppb is equal to 10 power minus 6 gram per liter. So it is 10 into 10 power minus 6 gram per liter divided by C2 is 10 into 10 power minus 6 in 10 power minus 6 minus 0. So when we multiply this I am neglecting this term, into 10 power 5. That is 2 into 30 is equal to 60. So the flow in the river will be 60 meter cube per second. So coming to the next question, what is the discharge over a... Okay, so now let's look into indirect measurements of stream flow, that is using hydraulic structures. Okay. So in case of hydraulic structures, we have discussed that we use thin plate wires and we also have broad crusted wires. The third type is flumes. These are the three hydraulic structures that we will use to measure the stream flow. Okay. So in case of thin plated wears, based on the shape of the wear, shape of the notch, we have different types of wears. First one is rectangular thin plate. Or sharp crusted wear. So in this, how we will calculate stream flow is discharge is equal to 2 by 3. CD is coefficient of discharge. G is acceleration due to gravity. B is the effective width of the notch. And H is the gauge head. Using this relationship, we will calculate the flow in rectangular thin wear. Okay. And if this width of the effective width by width of the channel is equal to 1, then we will call it as full width rectangular thin plate wear. And if B is less than capital B, it is called as contracted wear. In case of contracted wear, we do not apply coefficient of discharge. Sorry, in case of contracted wear, we also have correction coefficient which will be multiplied to coefficient of discharge. So next we have a triangular or V notch thin plate wear. Okay. In this, the discharge is calculated using the formula Q equal to 8 by 15 CD into root 2G tan theta by 2 to H power 5 by 2. Here the same term, CD is coefficient of discharge, G is acceleration due to gravity, theta is the angle made by the triangular notch. Whatever is the angle here, that is called theta, that is angle of notch, and H is the gauge head. Okay, if the notch angle is 90 degree, then that's the mostly used type of triangular notch. Okay, and we also have trapezoidal weir, which is a combination of one rectangular and two triangular notches. And so that's where the formula will be rectangular plus triangular notch. Okay. Okay, and the special type of trapezoidal weir is Cipollati weir, in which the side slope is maintained as a 1:4 ratio. So the contraction coefficient in this case will be 1. Okay, that's the advantage of Cipollati weir, but it's very difficult to maintain the side slope. So then we have a broad crested weir, which has a wide flat crest that spans across the width of the channel. Okay. In this, the discharge is calculated using the formula Q equal to CDLH. CD is coefficient of discharge, L is length of the crust, small h is height of water over the crust, and capital H is height of the water head. Okay. Or this is also equal to 1.7 times CD into LH. Okay. In case of flumes, the construction in this flumes are constructed by constriction in the channel by narrowing in the channel or a hump or both. Okay, so the advantage is we can get a continuous flow measurement, and also the capacity to transport sediment and no requirement of loss of head and minimal risk of submergence in case of flumes when compared with weirs. Okay, so in flumes also we have three different types. Mainly we will be talking about two types, partial flumes, which will operate with a small drop in head, and it will adopt a ventricular Venturi principle. So in this case, the loss of head will be 25% of the loss of head in the case of weir. So also we will have some converging, diverging, and also a throat section within this flume. And the discharge is measured as Q equal to K into H power U. K is the dimension factor and it is a function of throat width. And generally U value will vary from in between 1.5 to 1.6. And the second type of flume is cutthroat flume, where here it's a simplified version of partial flume, and it doesn't have a throat section. It has only converging and a diverging section, and the flow is measured using the formula Q equal to C1 into HA power N into L. C1 is free flow coefficient. HA is upstream depth of flow. N is exponent, and it is a function of flume length. Okay. And now coming to indirect method of stream flow measurement, we have a slope area method in which we can see that the cross section area and the slope of energy gradient is measured, and we consider that energy equation for a non-uniform channel will be head loss equal to Z1 plus V1 square by 2G minus Z2 plus V2 square by 2G. So energy loss slope is equal to HF by L. That is the length of the length between the two sections. Okay. In slope area, we have main assumptions like the flow should be steady and uniform flow, and applicability of Manning's equation. We neglect sediment transport, so it is applicable to open channels. So in this, flow is measured using the formula Q equal to 1 by N into A bar R power 2 by 3 and S power 1 by 2. Okay. So this is popularly known as Manning's formula. Okay. Where A bar is the average cross section area of channel, R is hydraulic radius of channel, which is equal to A bar by P. P is the wetted perimeter of channel, and S is bed slope, which is equal to capital H by L. H is fall of water surface over the length of the channel, and L is the length between the two cross sections. Okay. So in case of non-uniform flow, the average convergence is taken as K equal to root of K1 into K2. Okay. And convergence is generally defined as 1 by N into A bar into R to the power of 2 by 3 in case of uniform flow. This one is in case of non-uniform flow. Average convergence is calculated like this. We'll find convergence at section 1 and section 2 and take a square root by multiplying both. Then we'll get average convergence. Okay, now let's talk about flow duration curve. Flow duration curve is a curve between percentage of exceedance and discharge. It will help us in designing structures on river and flood risk assessment, to evaluate ecological health, also to study sediment transport. Okay, this is flow duration curve. And next we have one more curve called flow mass curve, which is a relationship between time and cumulative flow volume. So since it's a cumulative, it will be an increasing function, and this is, we can see a hump here, which is a peak flow in that particular relatively months, and this is valley. You can see a depression. So this is a lean flow. Okay. So the cumulative flow is calculated by integrating the flow from the lower limit to the time t, and this lower limit generally will start from 0. Okay. And if we take 2 points in the flow mass curve and join them, the slope of this line will be giving us average rate of flow between these 2 points. Okay. So generally we will apply flow mass curve to determine storage capacity of the reservoir and also average flow for a particular period. and this average flow is called as supply line. Okay, and here in this figure we can see that in a dam what we will do is we have a dead storage which generally won't be carry on to the downstream, and we have an active storage or useful storage which we will be using for water supply and other uses like for irrigation or water supply. We will generally use this water active or useful storage, and we will have some more storage capacity, that is flood control storage. So whenever there is flood, no, the water will be stored in this part so that it can prevent flood in the downstream. And we will be keeping some more just for the for a safety precaution. We will give some more um, depth to accommodate the excess flood that is occurring. It is stored as surcharge storage. Okay. So if the water exceed this, the water exceed the flood control storage, the water will flow over the spillway. And then here we will be also talking about the reservoir storage and demand. So it's very important to know how much of water we need to always store in the reservoir so that uh, when there is low flow or in case of dry season, we will know we still have to supply the same amount of water. But if we don't store the water, then we won't know how we won't be having enough water for the supply, right? So that's why it's very important to always calculate the how much of water to be stored for the dry season and how much of water we can supply during a particular month or other or other cases. Okay, so if the supply is more than demand, then no storage is required. But if supply is less than demand, we need to store water in the previous month so that it can accommodate this demand in this particular month. This is called as lean period. And when the supply is more than that, it is called as peak period. So first we will have a graph between cumulative supply and demand versus time. So this red line is the supply across the time, and the black line is the demand. So when we are trying to find the amount of storage that is required, we'll just take, suppose we have a constant demand of 50 meter cube per second. Wherever these humps are there, we will draw a line tangential to this hump with slope of 50 meter cube per second. Okay, and we will calculate this maximum difference at each point. Okay, this maximum difference, the maximum of these values is taken. This will be the minimum storage that is required in a reservoir, is equal to maximum of sigma of Vd minus Vs. Okay, Vd is cumulative depth and Vd is cumulative demand, Vs is cumulative supply, and this minimum storage required is also called as maximum cumulative deficiency. So suppose, and the one more thing is like if you know how much of water is stored in the reservoir and if you know the demand, how much is the maintainable demand? That we need to calculate. The maximum firm demand that can be maintained by the reservoir is called as firm yield. So in this case, what we know is that we know the supply curve, the red line, and we know the storage, right? So what we will be doing is at this values, based on the storage value, we will draw a vertical line, and we'll draw a tangential between the hump of this supply line to this connecting to this point. So the slope of this will give us the demands. So in each sections we will do that, and maintainable demand will be equal to minimum of this DIs. Okay. So DIs can be calculated by the slope of this tangent, which is passing through the hump of the supply curve, and also a point which is an which will be obtained by adding this valley point plus the storage. Okay. And when we have a variable demand, how to calculate the storage? So suppose when we have a variable demand, the demand will change across the time period, right? We will have a cumulative demand curve, and also we will have a cumulative supply curve, and we will take the difference between that, whichever is the maximum difference, negative difference, that will be our storage required. I hope this is clear. Do you guys have any questions in this part? Flow duration, reservoir storage, and demand. How to calculate reservoir storage, demand. No questions? Okay. So let's look into few problems. What is the discharge over a rectangular notch over an angle of 90 degrees? Uh, so, sorry, this is rectangular notch. So the rectangular notch has a head of 0.3 meters and width equal to 1.2 meters, and the coefficient of discharge is 0.62 meters. So how do we calculate discharge using a rectangular thin wire? It's Q equal to 2 by 3 CD times root 2G P power P into H power 3 by 2. So by substituting the values, width of the notch is 1.2 and gauge head is, so once you calculate, the value is 0.3608 cube per second. Okay. So in a supplementary wire wear contraction, the correction is considered. First option is on both sides. Second option is on one side, and the third option is contraction correction is not required. And fourth option is none of this. The answer is contraction correction is not required. It's not required, but the main disadvantage is that we have to maintain a side slope of 1:4 ratio. The next question is to check whether the flow in a partial flume is submerged or not. The head is measured at option A converging section, option B throat section, option C both A and B, option D none of this. So the answer for this is option C, both A and B. We need to measure head at both the section to know whether the partial flow is submerged or not. So the next question is, which one of the following is not an assumption of slope area method? So the first option is unsteady flow, second option uniform flow, third option is applicability of Manning's equation, and fourth option is negligible sediment transport. So we have seen that in slope area method, the first assumption is the flow should be steady. So the option is A, and they're asking what is the, how do we plot flow duration curve? So flow duration curve is a plot between percentage of exceedance and discharge. Right. So they have given options. A is Percentage of non-accidents and discharge. B is percentage of accidents and discharge, which is our answer. C is percentage of non-accidents and stage head. D is percentage of accidents and stage head. Option B. So the next question is average flow rate can be obtained by joining 2 points in a hydrograph. B. Flow duration curve. C. Flow mass curve. D. Double mass curve. In flow duration curve, we have seen that it's a plot between time and cumulative volume. Volume of flow, right? So once we have this, when we join 2 points and get the slope, this gives us the average flow rate. So average flow rate can be obtained by joining 2 points in a flow mass curve. So coming to the final question. So they have asked us to compute a minimum reservoir storage required to maintain a constant demand of 50 meter cube per second, and monthly reverse flow to a reservoir are available as shown in the figure. So whatever inflow flow that is occurring in the reservoir is shown here. It's in mean flow in a month in meter cube per second is given, and so once we multiply with number of days, we will get flow volume in meter cube per day. So also we know that we have a constant demand of 50 meter cube per second. So in a month it will be 50 into 31 days. So this is the total volume that is required for January month. Okay, so basically this is flow into number of days. Using that we will calculate monthly flow volume. Here also in demand volume we are doing demand 50 meter cube per second into number of days. Okay, so if the supply is more than demand, we don't have any deficiency, right? So we first, if it is supply, if the supply is less than demand, we have a deficiency. So what we will be doing is to calculate deficiency. First we will subtract supply minus demand. So the column 4 and 5, for column 4 minus column 5 we are doing, and we are getting these values. So and next we are only considering the cumulative excess demand. So where the demand is more than the supply, only those rows we will be taking out. So all the negative values are given, and we will be doing cumulative. Okay, so here minus 1.55 plus minus 900 is the value in this second row. Like this we will add, and whatever in the consecutive days only we will add the values. Okay, so see here you can see there is a gap. So when we are calculating cumulative excess demand, we are not adding, doing minus 2009 plus minus 310, only we are taking 310 because there is a gap, it's not continuous. Okay, so whatever is the maximum value, that will be our minimum reservoir storage that is required. Okay, so and one more column is like we have cumulative excess flow where the supply is more than demand. Those values are written in this column. Okay, so here we can see that the at this stage in August month the storage in the reservoir will be 3100, which can be met by this deficiency. So within 2 months we can meet this deficiency, right? So that's how we calculate minimum reservoir storage required to maintain a demand of 50 meter cube per second. Mhm. So now we have in this lecture we have talked about the stream flow, how the water from precipitation will reach stream flow, and how it varies with the time. Also we have seen different types of ways the water will reach the stream flow, like you unsaturate the saturated excess rain, sorry, saturated excess overland flow, and Hattonian overland flow, subsurface flow, etc. And what are the types of streams? Also, how you measure the stream flow? Like we can first measure the stages and establish a stage discharge relationship. We saw different instruments which can be used to measure stages. Also, we have seen direct and indirect method of stream flow measurement, and we have also looked into uh, flow duration curve, flow mass curve, and how to calculate the minimum storage of reservoir and the variable and constant demand that can be met by a reservoir as well. So, if you guys have any doubts, you can ask me, or we can end this session. Any doubts? Okay. If we don't have any sorry, if you don't have any doubts, we will end this session then. Thank you for listening.